So it's a great pleasure to introduce Bob Weinberg. So actually, I don't have to say as much about the science because Dan introduced Bob during his talk. But Bob's known for many things. Among them, as Dan mentioned, identifying the RAS oncogene, which has been critically important, obviously for Dan's research and also for my research. So I'm excited to be able to introduce him. He's a professor at MIT, also one of the founding members of the Whitehead Institute. Has enormous number of honors. Among them, he's a member of the National Academy of Science, and in 1997 he got a U.S. Should I stop? I'm sorry. I'm being told to stop listing honors, so I'll let him go. Thanks.
Larry, can I tell a joke? Can I tell a joke? So I'm reminded of this Jewish joke where there's a small impoverished village in rural Poland, and one day they succeed in attracting a famous rabbi from Warsaw to come and give the Sabbath morning sermon. And before the teacher gets up, the president of the congregation introduces this famous rabbi and says he's learned it in 7 languages. He knows how to read 8 other ancient languages. He knows the Old Testament backwards and forwards by heart. He's an extraordinary human being and also known for his charity. And then he sits down next to the guest lecturer. And he looks at the rabbi, and the rabbi is visibly agitated. He says, Rabbi, great teacher, is everything okay? Rabbi, what's the matter? The rabbi says in a fury, you forgot to mention. He said, what did I forget to mention? You forgot to mention how modest I am. So I digress. Anyhow, I must say, listening to Dan Teodorescu's talk is for me very important because 36 years ago, my lab discovered the RAS mutation. And if I think back, as I have over the last 36 years, has there ever been any clinical benefit for human cancer patients? And the answer has been uniformly no. And Dan's talk is the first time after 36 years that I see the prospect, not the reality yet, but the prospect of there being some clinical utility. I'm grateful to be invited to this extraordinary seminar. It's the symposium. It's really a feast for the mind. I've learned so much. I changed dramatically the content of my talk, both seeing the fact that there are philosophers and historians and diplomats in the audience, and the fact that I teach freshman biology, and so I have a feel for what non-specialists can and cannot assimilate. And with apologies to those specialists who are here, I'll go into a little bit of background and go over from a view of 30,000 feet. Where are we in solving the cancer problem, and what are the roots of the problem? So, as many of you know, we all start out as a fertilized egg, and there's a whole series of cell divisions which leads ultimately to large numbers of cells in an embryo. And here we have large numbers of tissues, each of which has millions of cells in it, a whole succession of cell divisions that leads us. And by the way, for those of you who aren't necessarily believing in the tree of life, look at these embryos and you begin to appreciate how little has changed in the last 450 million years in chordate evolution. We'll get back to that as well. Right here is one root of the problem of cancer. And here's a micrograph of a human tissue. We see here perhaps 100 cells each with its own nucleus, the dark spot in the middle. Together, there are about 3 times 10 to the 13th cells in the bodies of each of us. And that's already a significant problem. But the real problem is that in our bodies and in the bodies of mammals, almost all of these cells are licensed to divide again after they've populated this tissue. In other words, none of them is absolutely prohibited from ever dividing again, and that represents an enormous liability. The reason it is that way is that it allows tissues to become self-healing, self-renewing. The other part of the fundamental problem with cancer stems from this kind of comparison. So here we are, there's 3 different mammals here. We're in the middle. We go through about 10 to the 16th cell divisions in a lifetime. That means 10 to the 16th of cells times cells grows and divides. A Thai bat which is the smallest mammal as far as is known, it has much shorter lifetime. It goes through 10 to the 11th cell divisions. And a blue whale, we don't really know, but the number could be somewhere on the order of 10 to the 20th cell divisions in a lifetime. And by the way, as an aside, I will tell you that the genomes of these three organisms are virtually indistinguishable. Nothing has happened in mammalian evolution for the last 160 million years, besides your genome, of course. So here is the problem. Each time cells go through a cycle of growth and division, there's an opportunity for disaster. And therefore, given the fact that we have all these cell divisions, this just represents an invitation for things to go terribly wrong. As you probably know, cells divide through a very complex process. Here's the process of mitosis, where one set of chromosomes ultimately divides into two sets of chromosomes. And this process is extraordinarily complicated. And it has so many pitfalls in it that it's a miracle it ever happens properly in any single cell. And we're going through, each of us, 10 to the 16th of these cell divisions in a lifetime. Here's what we looked like, at least here's what members of my family looked like 160 million years ago. So this is the way we started out. We were only about a centimeter long at the time, but already then, all of the genes and all of the proteins that are present in us today were already invented and were already essentially functional. And what's happened really is just changes in scale and slight changes in brain power, and Dennett would undoubtedly comment on this. But so the problem is that as we've grown from a mammal that's this big into one that's as big as we are, or a whale, there's been this extraordinary increase in the liability that something would go wrong during one or another stage of cell division to create damaged cells. And what are the liabilities that we're confronting? Multiple. Not only the problem of resorting chromosomes during mitosis, as I showed you before, but for instance, copying DNA, which has to happen each time a cell grows and divides. Here you see DNA polymerase, which is faithfully copying the DNA. And each time a cell divides, there has to be 6 billion copying events in order for there to be active and accurate replication with fidelity, in order that the daughter cells have exactly the same copies of DNA as do the parent cells. And in fact, this is almost perfectly proper. There may be 2 or 3 bases that are miscopied each time these 6 billion are copied. Here's what it looks like in actual physical life, we imagine, where the mother helix is being unwound and it's being recopied here. And this itself is also extremely complicated. Once again, there are multiple pitfalls for disaster here in this process of replication. Here's one of them, by the way. Here's a mother helix, here are the daughter helices, and here we have a break in what is temporarily transiently single-stranded DNA. And this is a very dangerous thing for the life of the cell, because more often than not, the cell has a hard time repairing such a break. And then there are lots of other pitfalls, other traps, death traps. Miscopying of the DNA, I just showed you this, where a T should be all right, it's a T here, but this was miscopied to a C. A segment of chromosome is duplicated. Another segment is entirely deleted here. And once again, this genome undergoes a whole variety of different degrees of mutation, and it's a constant struggle, ongoing struggle, to maintain the integrity of the genome so that the genetic information inside individual cells is proper, and that the cells receive the proper instructions as to when they should grow and divide. You might think that there's a master regulator of cell division located somewhere in the body. But the truth is, each cell in the body, with its own genome, is the master of its own destiny. It doesn't consult all the other cells in the body. It consults its own genome and its neighbors. And therefore, if its instructions are defective, then it's going to start misbehaving. It may die, or it may start replicating inappropriately, and that's right there the roots of cancer. Here you had other sources of damage, going to tanning salons. You can see ultraviolet light, or as we used to call it in Pittsburgh, ultraviolet light. X-rays. Here we have a number of mutagenic compounds, chemicals that react with DNA and actually damage its structure and thereby corrupt its information content. And there are tens of thousands of events in a single cell in a given day where the basis spontaneously lose part of their normal structure and thus information content, which loss has to be rapidly restored lest the cell begin to accumulate other mutations. And here are some of the whimsical different changes in information content which occur when one miscopies these bases. And we needn't go into them. Suffice it to say that in one way or another, a cell relies on the integrity of its genome in order to choreograph its own proper behavior. And therefore, what we have here, in the case of certain kinds of mutant cells, is a normal tissue. Here you see a micrograph of a normal human tissue. There may be 100 cells here, and they're collaborating in a condominium cells where each cell is constantly consulting the needs of its neighbors in order to create an architecturally well-structured and thus functional tissue. And this is what happens in cancer, where a single cell here or there has an altered genome, and it begins to replicate uncontrollably. And now, rather than paying attention, paying heed to the needs of its neighbors, it has only one agenda item, which is to make more copies of itself. And that's the essence of cancer here. Here's the retina. By the way, this is extraordinary. What fraction of human beings are born sighted? 99%, 99.5%. If you look at the extraordinary complexity of the retina, you think about those things, it's highly improbable. How could the eye ever be formed in any human embryo? And yet we all are born with these layers in the retina. And here is retinoblastoma, where a single one of these cells starts growing uncontrollably and goes off on its own. Here's yet other things, and here you see these carcinomas. Here's a normal epithelial tissue carcinomas. And note, by the way, that these cells in the carcinoma try to recapitulate the shape, the morphology of the appearance of the normal tissue. Even subtle changes in DNA structure can have catastrophic consequences for the growth of the cell. Here is the mutation that Dan was talking about that was discovered in 1982. And here we see that this DNA sequence is totally intact, save for a single base pair being changed from G to T in one base of this gene here. And here, this provides testimony to the powers of recombinant DNA and DNA sequencing, which already in 1982 allowed one to fish out a single DNA base change out of the 6 million DNA bases that were present in the bladder carcinoma in which this was discovered. And this, of course, is only multiplied in the years that have followed, but we now have the power to map out all of these mutant genes. And here's what happens in the life course of a human cancer. This happens to be a colorectal carcinoma, as was puzzled out in Johns Hopkins, 1989. And what we see here is, first of all, that looking under the microscope, there are a series of stages where a fully normal cell, microscopically in its appearance, acquires more and more and more aggressive traits until ultimately it forms a primary tumor here called a carcinoma. And then that carcinoma will, with a certain probability, it may or may not invade and metastasize, and 90% of human cancer mortality is associated not with the primary tumors, but with the metastases, whose production we don't really understand that well. And obviously Dan just provided us with a very interesting insight into how they may form. So this is an interesting question. It takes a long time. I often say that in most of us, each of these steps may require 10 years. And I tell my students, if you go to McDonald's every day, and have a Big Mac, you could compress this to 2 or 3 years for each step, and therefore have it happen much more quickly. But normally it takes a long time to happen, and that's part of the reason why we're not all covered with tumors all the time, because there are barriers to this progression going from here all the way over to here. These different mutations, which not only accompany these different histological stages, these changes you see under the microscope, but also drive the changes in cell behavior. These are the critical drivers of the increasingly aberrant behavior of cancer cells. Each of us, right now, in this auditorium, has between 10 to the 5th and 10 to the 6th cells scattered throughout the body, which have this RAS oncogene mutation. I showed it to you before. And some of you might be much unsettled by this. If you were to look hard enough, you'd find maybe 1 million cells throughout the body with this mutation, and yet we don't end up covered with tumors by the age of 3. This only testifies to the fact that this mutation may be necessary to form a tumor, but it's not sufficient. And if it were sufficient, then we would all be covered with tumors by the age of 3. And therefore, our cells are hardwired up that if you sustain a mutation like this, it may have a slight alteration in the behavior of a cell, but it is of its own accord not sufficient to create a full-blown tumor. So here is one solution. We don't know all the solutions to the problem of how our ancestors have dealt with the enormous increase in organismic size. Because if you look at a mouse cell, you can put 2 mutant genes into a mouse cell, and that suffices to transform the cell. By that I mean convert it from a normal cell into a cancer cell. 2 mutant genes will suffice to create a cancer cell. But if you look at our cells, it takes 5 mutant genes. And what that has meant is that during our evolution as a large, long-lived mammal, we have acquired a whole series of defenses so that the hardwiring of our individual cells makes it much more difficult, erects far more impediments to the formation of a human tumor. And this is one of the reasons why we're not all covered with tumors by the age of 3. Here's actually the epidemiology of human cancer. And here what we talk about is the incidence of different kinds of cancer. And what you can see here is that, among other things, to state the obvious, cancer is a disease of old people. See, you can see here's 10 to the 16th cell divisions. And by the time about half of these have happened, already one begins to see an uptick in a whole series of different kinds of tumors. They all behave pretty much the same, except breast cancer, which starts up earlier. And this, again, testifies to the fact that it's a long and complicated process for any human tumor to form. And this is also testifying to the efficacy of the anti-neoplastic defenses that are hardwired into our cells and tissues that prevents the outgrowth of a tumor. It does drop off up here, but this has recently been found to be an artifact. Sorry. The real old people also get cancer. And by the way, we don't really know how often whales get cancer, so I'll have to, that's a qualifier there. And I'm sure that was eating away at some people. Okay, so here, how long does it actually take for a cancer to form? And we don't really have a good idea. You might sense that each of us in our body has certain incipient cancers throughout our body, and that's almost inescapably the case. The question is, can we reach the age of 80 or 90 or 100 without those incipient cancers becoming full-blown and becoming clinically accessible? And if you were to look hard enough in each of our bodies, you'd find small nests of incipient cancer cells, which, the good Lord willing, will never progress through acquiring additional mutations to become a full-blown tumor. So here's the only really good, rigorous measurement we have of how long it takes to create a human cancer. In global cigarette consumption was down here in 1900. During the Second World War, the Defense Department issued cigarettes in the K rations of the GIs. And so cigarette smoking really took off. And here is the almost parallel curve of the deaths caused by lung cancer. It took exactly 30 years. So this is a really compelling, these two curves are totally parallel, and it's a compelling measurement of how long it actually takes. Most kinds of cancers, fortunately, take a lot longer. Here we're talking about lungs of people which are every day of the week are afflicted with hordes of chemical carcinogens which are being inhaled through the cigarette smoke. So this is an exaggerated, an accelerated form. So here is part of my message. How well are we doing? I often can talk about oncogenes and tumor suppressor genes and metastasis genes, and the audience, people in the audience say, well, doc, that's all very good, although I'm not a real doc, but what are you going to do for my great aunt who has breast cancer or something? So here I want to show actually how are we doing. And the news is not all bad. Colorectal cancer deaths have gone down. This is death rate now, by the way. And death rates you can't fool with. As I'll show you momentarily, incident rates are a cultural artifact. Stomach cancer, people are dying less and less uterine cancer, and this is a good thing. Now, it's interesting to know why these declines have happened. Well, colon rectum is colonoscopy. If you get colonoscopy, you can reduce the rate of dying from colon cancer by maybe 70, even 80%. So this part of screening is not bad. Uterine cancer, look at the declining rates. It's extraordinary from the Pap test. Also, screening is extraordinarily useful. Stomach cancer, look how it's gone down. A testimonial to the efficacy largely of food preservatives. So when you see all these organic foods that are being sold out here in Colorado, which have no preservatives in them, God forbid, think about this. Think about this. Stomach cancer in this country was the most common cause of cancer-related deaths 100 years ago. And now look what's happened. The horrible damage caused by food preservatives. Here are the other statistics, which are not so positive and not so encouraging. The big elephant in the room, obviously, is lung cancer. And you see it going up, and it's started to go down, males and females. Some cancers are pretty steady. Pancreatic cancer is going up, actually, a little bit every year. Ovarian cancer is pretty steady. Prostate cancer is it's going down a little bit, but there's not dramatic changes except for lung cancer. And it's useful, it's instructive for us to know what's the cause of these changes. The decrease in lung cancer mortality has nothing to do with the clinical oncologists, Dan notwithstanding. The decrease in mortality from lung cancers comes from the fact that people have stopped smoking. The decrease in breast cancer is real, by the way. The decrease in age-adjusted mortality in breast cancer is between 30 and 35% in this country. And that's not due to increases in the number of cases. It's due to the fact that actually clinical oncologists have grown very effective in treating the disease. And who gets the credit for this? Well, everybody's always fighting because, as you know, success has many parents. Failure is an orphan. So who gets all the credit? Chemotherapy is very effective. It has a marked contribution to reducing mortality. Hormone therapy, surgery, radiotherapy, and Herceptin. Amusingly, you may wish to know, or maybe you don't want to know, the contribution of this decrease made by mammography screening is highly questionable. So if you women have not gone to the mammography studio over the last couple of years, you could probably relax because it's not clear how much good it does. Of course, the radiologists will react with outrage because, after all, that is their daily bread. But we have to think about this. I don't say all screening is useless. I told you about the Pap test. I told you about colonoscopy. But in the case of mammography, who knows? How much cancer is there actually in our society? That's a pretty interesting question. You might say, well, we kind of know how much there is, but we really don't. Here we have these extraordinary imaging technologies, and we heard about them before from Microsoft. You'll confess to it, right? Look what they can see now. Tiny growths. So you must say, well, that's a terrific thing. But it is a mixed blessing, because here is the difference between mortality from breast cancer and the incidence of breast cancer. So the incidence is actually much higher than the mortality. And by the way, for your amusement's sake, I will mention the fact that here the mortality from breast cancer was totally flat for 60 years. It hadn't budged an inch, which you hardly see in any kind of human disease of any sort. And during this time, we were deluged with these reports that there was a breast cancer epidemic. You may or may not remember that. And here's incidence. So how much cancer is there actually? Breast cancer. Here is something useful, an interesting statistic. Every year, in 2017, 250,000 women are diagnosed with invasive breast cancer. And 40,600 women are going to, with great likelihood, die from the disease. So what's the difference between these two numbers? You might say, well, it's the brilliance of the oncologists, which are effectively treating all these tumors and reducing the potential mortality from here down to here. But there's another answer. And the other answer is, it's probably the case, and other people may take contention with this, that about 80% of the cancers that are diagnosed would have remained undiagnosed 50 or 100 years ago, and women would have died at the age of 80 or 90, bearing such tumors and never knowing that they had, quote unquote, breast cancer. I go to breast cancer meetings and women come up to me and they say proudly, I beat off breast cancer. And I hold my tongue, I bite my tongue because I'd like to say to them, but I don't. Chances are high that you had a form of breast cancer that wouldn't have killed you in the first place had it never been diagnosed. But I don't say that because it's not politically correct or acceptable for whatever reason. So this creates a major problem because right now we're aggressively treating, and Dan is a much better testimony to that than I do, we are aggressively treating all kinds of breast cancers, whether or not they have the prospect of actually leading to a fatal outcome. Here you can see one trait of this. Here are distant metastases at diagnosis, distant growth, and these are the killer tumors, the metastases, we've heard of it. Here are localized tumors. You see they've been going up and up over the years. And these are the tumors, many of which are with great likelihood not going to affect the lifespan of the involved patient. If you ask women walking down Main Street in Cambridge, Massachusetts, what are you going to die from? 60% of the women say, I'm going to die from breast cancer. What fraction of women actually do die from breast cancer? 3%. So there's a disconnect between what we perceive and what's the reality. Prostate cancer is equally, it's a mirror of what I just told you. Here, by the way, is the incidence, and here's the mortality. And you notice this spike here, which illustrates most amusingly and dramatically how much of a cultural artifact incidence is, because this was a year where somebody infamous, it wasn't the wife of a president, but it was the president, or somebody important, was diagnosed with prostate cancer. Right away, everybody went and had their prostate diagnosed, and there was a big spike in the incidence of the disease, which of course is just a cultural artifact. Here's what happens if you look upon autopsy at the prostate glands of men in this country. And by the age of 80, it is said that 80% of men have prostate cancer. By the age of 90, upon autopsy, independent of the cause of death, almost all men have prostate cancer, as looked at under the microscope. What fraction of men die from prostate cancer? Well, the number is, once again, about 3%. So this represents an extraordinarily difficult problem in terms of the economics of healthcare delivery, because we're treating everybody one way or the other, because we don't, God forbid, want to risk malpractice in not treating a man or a woman who somehow was not aggressively treated after diagnosis. Here's my favorite case, melanoma. We've all heard about the melanoma epidemic, and people do get melanoma and die from it, especially, by the way, redheads. There aren't that many in this audience, but like in Australia, they have lots of them. And here is the melanoma epidemic. And here you see total incidence of the disease, how often it's registered, and here is the mortality. Look at that. Once again, totally flat over a period, in this case, of 15 years. What's going on? And by the way, here's the incidence of early stage disease, very shallow lesions. And you see the number of them is going up at a great rate. And here, so there was if I may use the word, there was a smartass at Dartmouth Medical School, excuse my excursion into semi-profanity, okay, who did the following, an iconoclast. He went across the country and he asked, how often do people go to the dermatologist for screening? And it turns out that in New York, they go every 2 weeks because they're all hypochondriacs. And in Montana and rural Colorado, they never go because they're tough. And so there's an extraordinary difference in the frequency of the visits in different parts of the country to the dermatologist. And then he asked, what's the incidence of the disease in different parts of the country? And that's plotted up here. And look at this here. It's a straight line. Wow. The more you look, the more you find. So think about that the next time you hear about the melanoma epidemic, and it just gives us a very important take-home lesson. We can no longer afford to deal with all these cases for reasons I will make clear momentarily, but we're already running up against a big iceberg. And I'll show you the size of the actual problem. Let's say the cancer annual death rates from different kinds of cancer is roughly constant, and it might go down a little bit over the next years, but let's say it's pretty flat. Let's say that cancer is a disease of old people. And by the way, just to emphasize something, we all know more and more people who've been diagnosed with cancer. Much of that is overdiagnosis, but some of it is due to the fact that some of us in the room are older, and we're reaching the age where our contemporaries are more likely to develop cancer. And cancer is, to a certain extent, a disease of old people as much as Alzheimer's is. We have to recognize and embrace that. It's not that there's an epidemic of cancer sweeping over the society. And the chances of any one of us dying from cancer now, if we don't smoke, let's say, are no greater, and probably are less than 50 years ago or 100 years ago. It's not that any one of us runs a specifically increased risk. It's that we're just living old enough to confront a disease of the aged. Here's the number of Americans over the age of 65 that are projected in this country. So if you put all those numbers together, you come up with things like this. This is the number of actual people who die from cancer over the next decades, and it goes up and up and up. Not because we're awash in carcinogens, not because we're leading terrible lifestyles, but because more and more people are reaching the age where they have to confront for the first time Alzheimer's on the one hand and cancer on the others. And it's not clear how we're going to be able to afford that. And I'm not competent to judge this, but the real GDP growth rate grows about 2% a year, but this rate is growing much more rapidly. And even the pharmaceutical companies are beginning to confront the reality that our economy will no longer be able to pay for all this. We're just going to run out of money. And nobody really has come up with a good solution for this. Maybe Larry Gold will with his SomaLogic company, or maybe not. So, nothing personal. I'm just telling you, we can agree it's a problem. Okay, and I promise no more jokes. Okay, so here I showed you this before, and here's what the microscopists see under the microscope. And so there's this progressive change in the behavior of many kinds of cells. And many different kinds of tissue sites behave very similarly. A progressive change in cells that look more and more and more abnormal. This is not an idiosyncrasy of the colon. It happens in lots of other tissues, which yield, for example, in this case, carcinomas from epithelial tissues. And so, as I told you before, but just to reinforce it, mutations really drive the increasingly aberrant behavior of these cells because the instructions they receive, each of these cells, comes directly from their own genomes, and their genomes are increasingly loaded up with bad directions. And over the last 40 years, we have begun to understand what goes on inside individual cells that illuminates why these mutations actually lead to runaway cell growth. And here's a simplified circuit diagram of what happens inside individual cells. And I will just tell you each one of these green circles represents a distinct signal processing protein. You heard from Dan earlier about a whole series of signal processing proteins. These proteins talk and signal to one another within the cell. And here you see the protein that Dan talked about. And here you see how signals are processed in the cell because an individual cell needs to compile all this information and integrate it and come out with a decision. Should that cell divide or remain quiet? That's a decision cell has to confront every day of its life. And here we see some of the mutations that are found in certain kinds of human tumors and how there's subcircuits in these tumors which are perturbed by changes in, for example, this oncogene which Dan talked about. This is another oncogene involved in small cell lung carcinoma. This oncogene gets perturbed, gets inactivated in maybe 50% of all cancers. And so there's a whole series of short circuits that accumulate in a given human cell that lead it to misbehave. And to repeat something I said before, there needs to be 4, 5, 6, maybe even 7 of these short circuits in the cell as a whole, in the circuit as a whole, before a single human cell will begin to grow uncontrollably. And by the way, 40 years ago, we knew nothing about this, and now we know enormous details about it. And one of the things we learned, by the way, is that this circuit is essentially unchanged over the last 150 million years. So the complexity of it is not an artifact of modern civilization. All of the solutions to the problem of how to build a complex organism like ourselves were already worked a very long time ago. And here we see how these different genes perturb and disrupt and short-circuit different components of the cellular circuitry. This is an image that was created by a biotech company which hoped to be able to understand the behavior of individual human cells by drawing it out as a circuit diagram. Resistors, capacitors, transformers, and so forth. And so they drew up all these things. Each one of these is a signal processing protein. And the goal here was to be able to predict the behavior of a single human cell on the basis of how all these proteins were perturbed by different kinds of mutations. That was their goal. And they failed terribly because we are still decades away from being able to model the behavior of a single cell on the basis of this circuitry. It's extraordinarily complex beyond measure. It's a product of literally 1.5 billion years of evolutionary tinkering in Rube Goldberg contraptions. And we just have no idea how to understand how this circuitry will inform and educate a given cell as to whether it should commit to grow and divide or whether it should stop growing. And so these people and other people who are called systems biologists, they will say, well, just give us the outline of the circuitry and we will tell you, we'll be able to predict how a cell will behave. And I tell my students, if you ever hear that from somebody and you shake hands with them, count your fingers afterwards. Because they don't know what they're talking about. This is impossibly remote, vastly more complex than we have any way of dealing with it at present. So here, just to summarize what I've been saying, we're dealing with an individual, this is a cancer here, an individual cancer cell is there. Here is the circuitry informing that individual cell. Here is a critical gene, which may be disrupted, a gene and protein in that cell. And here, and you saw some of the elegant molecular biology that Dan Theodorescu was able to mobilize before. We can look at the protein, the three-dimensional structure of the protein that one can create. And here one can actually create a molecule which is able to fit into that protein, we saw that before, and shut it down. And that's an extraordinary achievement. And in fact, it represented the poster child of personalized therapy because this represented the drug that was developed to successfully treat chronic myelogenous leukemia patients who otherwise were doomed to die in 3 or 4 years and now lead symptom-free lives of 10, 15, 20 years. Of course, they have to take the drug every day or two, much to the pleasure of Novartis. But in any case, they're doing just fine. The illusion was that this kind of treatment would be useful for a variety of other kinds of cancers. And so over the last 20 years, there's been a profusion of developments of a whole series of targeted drugs and personalized therapy. Here's just a summary of these things. Different drugs that have been developed in the way that Dan was describing. Each one of these developments, as his drug development has been, is a tour de force. Extraordinarily high-tech, extraordinarily challenging. And the problem with all this is as follows. The problem is that patients often respond to these treatments for 3 months, 6 months, 9 months. But unlike the chronic myelogenous leukemia patients, they relapse after 6 months or 8 months or 10 months. And sometimes we know what to do for them, and often we don't. And so the promise of molecular biology and personalized therapy, that it's going to totally revolutionize cancer mortality, has been a bit of an illusion, unfortunately, with all good intentions notwithstanding. And we don't really know how to deal with that right now. Tumor DNA sequencing, here I take a slight difference with Dan. The sequencing of human tumors has been reported by some, to be really the answer to the cancer problem. If we sequence the genomes of human tumors, we will really be able to understand how they behave and how to treat them. And the fact of the matter is there are some inconvenient truths here. First of all, a relatively small proportion of patients, I don't know, maybe 15 or 20%, are actually helped today by sequencing their tumor genomes. But there's another inconvenient truth, which ends my talk here today, which is focused on my own work. And that is the following, that if we look at the behavior of individual cancer cells, we find that we cannot intuit their behavior on the basis of their DNA sequence. So here we see an example of this. These are pretty benign carcinoma cells growing in a mouse. Here's the mouse tissue. Here are carcinoma cells, which are pretty benign, and they're red. And these cells flip over from being in a good state to being in an aggressive state, going from red to green in response to signals they're getting from the mouse cells. And it's called an epithelial-mesenchymal transition. These are the good guys, these are the bad guys. And here all these cells are flipping from a good state to a bad state without any change in the sequence of their DNA. And this is called an epigenetic or non-genetic change. And in my mind, to my mind, the majority of the traits, of the innumerable traits of a human cancer cell, cannot be gleaned by sequencing its genome. And that's a bit of an embarrassment for those who've touted DNA sequencing as the be-all and the end-all. I wish they had been correct, but it ain't so. And we haven't really begun to understand how to integrate the behavior of non-genetic mechanism, this is an epigenetic mechanism, with the sequence information. We don't really know how to do that now, and it's still an illusion. So here we are now, 1971, Nixon signs his war on cancer thing, and cancer was going to be cured definitively in a lifetime. We had an NCI director called von Eschenbach who promised it would all happen in 5 years. Whatever. And here are the age-adjusted death rates from cancer beginning in Nixon's war on cancer. And it hasn't really changed that much if you look at this. And it turns out that all good intentions notwithstanding, given the vast horde of people who have been working on cancer, as one says about me and others, more people are living off of cancer than dying from it. It's a bit of... We've worked hard. We've been serious. Some conspiracy theorists say we don't really want to find the answer, but we really would like to. And it turned out to be much more challenging than any of us could have anticipated. And the one take-home lesson that you may have gleaned indirectly from what I was saying is that if we're going to have significant reductions in cancer mortality over the next 10 to 20 years, the biggest reductions are not going to come from the whiz-bang molecular biologists and oncologists. The biggest reductions are going to come from changes in lifestyle. If we didn't smoke, we didn't eat red meat, we stayed lean, got exercise, ate a lot of veggies, one could probably reduce the death rate from cancer by 50 to 60%. That's not trivial. If what Dan works on and I work on, if that succeeds in reducing the death rate from cancer by 0.5%, we would be ecstatic. I just said 50%. So, and we don't like to talk about prevention because it's psychological, deals with consciousness, behavior, and that's messy. We like to talk about molecules and genes, which is intellectually much more satisfying and doesn't involve messy behavioral psychology. But in the end, it's going to be that which is going to make the big inroads in human cancer. And so on that note, I thank you for indulging me today.
It looks like Larry's chomping at the bit for a question. No, am I wrong?
There's no rush because there's no one after you.
Yeah, no, but these people are hungry, hypoglycemia, hunger, fatigue,
I would like to
overload.
Yeah, I get it. I wonder if you would take a few minutes,
Yeah.
not 30 seconds,
Yes.
because you didn't mention it, to tell us your view of the role of tumor mutational burden, because you said something a little frightening about the more aggressive tumors having higher tumor mutational
Yes.
burdens. And that is, as I now have learned, the best sign for being treated with the new immune enhancements. And
Yes.
if you would explain that
Yes.
to this audience, I think they would be grateful.
I'd be pleased to do so. So I've depicted the mutations in the genomes of human cancers as being generally a malignant attribute of the cancers. The more mutations in critical growth regulating genes, the worse the cancer is going to behave. What I didn't say is that mutations strike the genome randomly in critical growth regulating genes and all other kinds of genes scattered throughout the genome, which ultimately have little say in the behavior of the growth or non-growth of the cancer cell. One of the side effects of these mutations is to create mutant genes which may not perturb the growth control of the cell, but they may cause that gene to make a novel, slightly altered structural protein. And that novel protein is something that excites the attentions of the immune system. Because as our immune system develops, our immune system becomes tolerant of all of our normal proteins. Otherwise, if it were to start to attack our normal proteins, we would all have autoimmune diseases. Rheumatoid arthritis is one, lupus is another one, and that would be very bad. So our immune system is generally tolerant of familiar proteins. And it doesn't attack cells that actually have these familiar proteins. But these cancer cells inadvertently acquire genes that make altered proteins. The altered proteins probably have no effect whatsoever on the growth of the cells because they're striking genes elsewhere in the genome, but they can alert the attentions of the immune system because the immune system now recognizes cells that are producing structurally aberrant proteins. That's what the immune system is good for. And recently, over the last 5 years, really, over the past decade, one has developed ways of activating the immune system so that the lymphocytes, the T lymphocytes as it were, which attack cells throughout the body, the lymphocytes are now unleashed so they can attack cells that actually are expressing aberrant proteins. And this works brilliantly in the case of certain cancers, like melanoma, by the way, or like colon cancers, which have large numbers of these mutated genes, which are producing what are called neoantigens. A neoantigen is an antigen, is a protein which is not present in normal cells, but is just the invention of a cancer cell as a consequence of a rare and random mutation. And so having more mutated genes can actually be good if one is able to mobilize the actions of the otherwise ineffective immune system to attack the cancer. And so we now have what's called checkpoint immunotherapy, and it's been quite brilliant in really curing maybe 30% of melanoma patients, lower cure rates in other kinds of solid tumors. But this is the beginning of a hope that perhaps we will figure ways of unleashing the immune system so it can attack a whole disparate array of recently arisen cancers by recognizing their neoantigens. We don't yet know at this stage whether this checkpoint immunotherapy will eventually prove to be applicable to a wide variety of human cancers, or whether it's going to have narrow applicability. Obviously, people who are invested in immunotherapy of cancer have a certain point of view. I take a more distant view of the whole issue. But it could well be that we have an entirely new way of dealing with cancer, not by developing drugs, which we can hope will be highly effective, but a way of unleashing the attack by the immune system on cancer cells that express aberrant proteins. Is that the 2-minute explanation you wanted, Professor?
So as Larry pointed out, this is your chance to ask a question, since the only thing after this is, okay, we have one more, and then we'll wrap up so people can wander.
I have a question about P53 and the complexity of the whole system, and it's sort of a razor's edge, really. So I have an interest in Parkinson's disease.
Just to interrupt, P53 is an alarm signal protein in the cell. And P53 is designed so that if the cell senses damage to DNA, damage to its metabolism, hypoxia, P53 may actually become activated in the cell and kill the cell so that it does not continue to grow in an aberrant fashion. So it's the alarm protein in the cell.
Right.
Madame.
So in Parkinson's, it's highly upregulated, and in a number of other neurological diseases, it's highly upregulated.
Yep.
So, if you try to upregulate that to treat cancer, do you end up over the other side of the razor's edge in some kind of autoimmune or neurological problem?
Well, I can't address that. I don't know how P53 behaves in autoimmune diseases. Unfortunately, there's not been a good way of drugging cells which have aberrant p53 to date. And it could be that p53 turns out to be very useful in terms of manipulating progressive Parkinson's disease. By the way, in defense of myself and my compadres who've been working for 40 years with relatively little to show in terms of clinical efficacy in clinical oncology, it should be said that the major advances in neurobiology and the major advances in immunology were all based on the discoveries that the cancer biologists made about the circuitry of cells. So the next time you hear that the cancer researchers are useless louts, please know that we can actually claim credit for having laid out the roadmap inside cells for how the immune system works and how neurobiology works and how many other systems work, maybe even those involved in Parkinson's. And on that dramatic note of self-justification, thank you for having me.